Okay. Finishing up chapter 4. In the 2 and 3 dimensions section. So we're going to look at these last 3 sections today. So in here, projectile motion is the type of motion that occurs when we have only one type of acceleration, and that is acceleration due to gravity. And that's considered projectile motion. There's modified projectile motion with like air drag or air friction, however you want to think about it. But for now, we're going to just talk about an object that is launched into the air somehow. And after the force that has launched it has finished doing its thing, we get projectile motion as the object travels in 2 or 3 dimensions, depending on how you set up your coordinate system, under the influence of just gravity. So gravity is the only thing that affects it after it is launched somehow. So here we have the example of a soccer ball being kicked. After the ball is kicked, if there's no air friction here, we're going to consider this motion of this ball projectile motion. Now, the acceleration due to gravity will be negative 9.8 meters per second squared, negative being towards the ground, towards the center of the earth, in other words. Acceleration in the x direction, of course, will be 0. So we've already got that all set up. Our acceleration vector is known. Because there's no acceleration in the x direction with projectile motion, all of our kinematic equations in the x direction simplify down to just one, and it's this one right here. Essentially, all the equations either tell us that our velocity initial is equal to our velocity final, except for one of them, which is the first one, which tells us the final position equals the initial position plus the velocity times time. So all the other ones just boil down to, because the acceleration is 0, just boil down to the velocity is constant. And with that constant velocity, we can calculate the final position if we know the initial position and the time. In the y direction, we remain with all of the kinematic equations. And in particular, these 4 kinematic equations are useful. And in place of acceleration in the y direction in each equation, we have negative g, negative g, negative g, right? Where g is 9.8 meters per second squared. So the interesting thing about this is that we only have the one equation in the x direction, but we also know a lot of things about the x direction. And in the y direction, we have all the kinematic equations at our fingertips. But between those equations in the x direction and the y direction, we have something that is the same in both directions. What is the same in both directions in the kinematic equations? Here's our kinematic equation. Here are the 4 kinematic equations in the y direction. Here's the one kinematic equation right here in the x direction. What is the same between them? What do they have in common? It's like that Sesame Street song. Which one of these is like the other? Whatever. Anybody have a thought? What I'm really asking is, what parameter or variable in all of these equations Well, in the equations that are in y and versus the equations in x, which parameter or variable is in both? Time, right? Time doesn't care about dimensions, right? Time is just time. And so if you can find the time in one of the dimensions, that can be very useful. You can use it in the other dimension to find other things. So that's a really important thing to realize. How do we go about doing this? Well, it's the same as doing it in two dimensions, except in one dimension, except you just have to do it twice, once for each dimension. And there's the additional step of whenever you're dealing with two-dimensional or three-dimensional vectors, the additional step at the very beginning is to break down all your vectors into various components in the different directions, and then kind of split them up into different problems. So you're doing a problem that just deals with the x components of the vectors, doing a separate problem for the same problem that's just dealing with the y components of the vectors. And if you have z components, then you do the same thing for z. But you're solving equations in three different coordinate directions, or cardinal directions of your coordinate system. And sometimes you're doing that simultaneously. You might solve for t in the x, components of your vectors, and then use that t to solve for velocity y final in the y components. Whatever. So you can move back and forth as you learn things. Also, when you break down your components, you break down the vectors into the components, you will find that other things are shared across the equations, because you start adding variables into the equations. And the magnitudes of the vectors, for example, are shared across the equations. The angles are shared across the equations. And that also can be useful. So let's do an example here. A fireworks projectile. We're going to fire a shell into the air, a fireworks shell into the air. We're going to give it an initial speed of 70 meters per second, an angle of 75 degrees above the horizontal. The fuse is timed to ignite the shell as it reaches its highest point. We want to calculate the height which the shell explodes. We want to know how much time it takes for the shell to get to that highest point and explode. We want to know the horizontal displacement. Or in other words, how far downrange it is when it explodes, how far in the x direction it explodes. And then the total displacement from the point of launch to the highest point, so the height that it travels. So here's the picture that we're dealing with here. They've actually given the answer, but we don't know that yet. And we have this shell being launched, the initial velocity being naught, goes up to the highest point and explodes, angle 75 degrees. So we're going to break things into components. We know that the x direction acceleration is 0. We know that the y direction acceleration is -g, right? They go ahead and define the initial x position and the initial y position to be 0. Where you choose your origin is completely arbitrary. So they're going to choose where it's launched from to be 0, 0. So x0 is 0, y0 is 0, and those are two things that are in the equations. So that's nice. In part A, we're talking about how high this thing is when it explodes, and that height is above the point where it started, which was the 0. But we also know that in the y direction, this movement is going to be at its highest point when the velocity is equal to what? What happens to the shell's y direction velocity when it reaches its highest point? It goes from going up to going down, but right at that point, what is it doing when it changes from going up to going down? It's stopped, right?
It explodes.
Well, it explodes, but what does the velocity do? The velocity stops. Yeah, for instantaneous moment, it stops. It's equal to 0, right? In fact, the firework still moves after that. It's just moving in pieces, right? And it's true. In fact, the center of mass of the firework will actually start coming down after it explodes. Just some of them will be going up and some of them will be going sideways and some will be going down. But if you track all those pieces and track the center of mass of the firework, it will actually follow a parabola still. So the explosion of the firework doesn't actually affect the overall motion of the center of mass of the firework. It doesn't really do anything to it at all. But at that top of the height, the velocity is 0. And so we can actually use that as our final velocity in the equations. We can say that our initial velocity is 70 meters per second at an angle of 70 degrees. And we can break that down into a vertical part and a horizontal part because we know the angle. And then we can say the vertical velocity, v sub y final, when it explodes is 0. Because that's what it has to do if it's going to change direction from going up to going down. And then we look for an equation where we can solve for the height. It just happens to be the last kinematic equation in the y direction, where we know where we have the final velocity equal to the initial velocity, both of them squared. And then we subtract off 2 times g times the change in height, where we know the initial height is 0 and the final height, y, is what we're looking for. We know the final velocity is 0, so we can go ahead and plug that in. And then we solve for the final height, which we don't know, y, and we get this formula. Now, again, I can't stress to you how important it is to solve these equations symbolically before you plug any numbers in. In this case, they plugged in 2 zeros, which made it easier to solve, and that's totally fine. But don't plug any other numbers in besides zeros. Because once you plug in numbers and then you make a mistake in your algebra, it's harder to find it. Here you now have a formula that you can not only plug numbers into very easily to get an answer, but you can also check it for errors as you go back the steps and see what you did algebraically. You can also use this equation multiple times with different numbers, which is nice. So you've created a formula that's very useful. When they go ahead and plug the numbers in for this, they have to plug in the initial velocity in the y direction, which is the y component of the initial velocity. So they have to actually calculate or figure that out, right? If we look at our picture back here, the y component is going to be opposite the angle of 75 degrees. So we're going to associate the sign with that, with our initial velocity of 70 meters per second. So initial velocity in the y direction ends up being v naught sine theta, which is 70 meters per second sine 75, so that's 67.6. Plug that number in along with g into this formula we created, and you have a final height of 233 meters. And if you've ever been to a fireworks show where they're using industrial fireworks, you know that's totally reasonable. 233 meters above the ground is pretty normal. In part B, they want to know the time it takes to get there. Well, now we know the final height. We also have numbers for the initial height and initial velocity of 0 all in the y direction. And we also know gravity is our acceleration. We can go ahead and pick another kinematic equation. Because we have one more thing, which is the final height, we'll have more equations to choose from. In this case, we're going to choose the second kinematic equation, where we're calculating the final velocity equals initial velocity minus g times t, the final velocity again being 0, the initial velocity being the 67.6 meters per second, and g, of course, being 9.8. We rearrange this, so we're solving for t, and it's just simply initial velocity over g, and we plug those numbers in, we get 6.9 seconds. Again, that's also reasonable. If you've ever been to a fireworks show, you can hear when they launch the shells. It's that that you hear at the beginning. And then you can actually follow the track as it goes into the air. Some of them easily take several seconds to get to their maximum height. So that's also quite reasonable. You could also use the third kinematic equation to do this because it also has t in it. And it would give you the same answer, and that's fine if you want to use that. Actually, this was the first kinematic equation they listed. You could also use the third one. This is the first one. We used the second one. We could have actually used the third one, but it's quadratic, so why would you? It's a messy equation. Who wants to use a messy equation, a quadratic equation? But so we used the simplest one. Then once you know the time that this thing is in the air, it's extremely easy to calculate the range downfield, or in other words, the distance it travels in x. That's just the only equation that we have for x, which is x equals final position equals initial position plus velocity times t. And that simplifies down to here when our initial position is plugged in as 0. And then you just solve for t and plug in your x component of your velocity, which is v naught cosine x, or 70 times cosine 75, 18.1 meters per second. Plug those in and you get 125 meters. Again, a very reasonable solution, very reasonable answer, and you're good to go. Remember that this is not taking into account air resistance. Air resistance will change things a little bit, but we'll get to that later. So if you want to know where this thing is, if you want to build the vector that tells you where this shell is when it explodes, then you take the x component of the position, which is the 125 multiplied by I hat, take the y component, or the height, 233, multiplied by j hat, add those two components together to get the overall position vector of this excuse me, of this fireworks shell. You can, of course, use the Pythagorean theorem to figure out the distance from its beginning point to its end point, or the magnitude of the displacement vector. You can also calculate the angle using the height over the horizontal distance and taking the inverse tangent, 61.8 degrees. Angle for the displacement vector. Notice that the angle for the displacement vector is not the same as the angle of the velocity vector. This thing was launched at an angle of 75 degrees, but the displacement vector is actually 61.8. Back here in the picture, you can actually see why that is the case. This is the initial velocity vector, the direction that they launched it, but the vector that we've just built is actually, get my drawing tools here really quick, maybe.
So it was 264 meters.
I think that's what it said, something like that. But the displacement vector is actually this one. So you can see this angle is obviously less than the original firing angle, right? Yes.
So if it's 264 meters, is the final displacement magnitude of the vector? That line you just
yeah,
showed,
that's the magnitude of the vector from the beginning point to the end point, which is the displacement vector. Incidentally, that's also the final position vector, because our initial position vector is 0. So. Coincidentally, I should have said. Okay. Here's another problem where they do a similar thing, except instead of having our final position in the y direction our final velocity in the y direction being 0, and our final position in the y direction being the maximum height of the projectile. In this case, we hit a ball with a tennis racket and we allow it to go up past that apex and then start coming down again. But it actually doesn't matter. The math still will calculate this. In this case, they tell us the final height of the ball is 10 meters. Oh, actually, I'm not sure what they tell us. Let's go look and see what it tells us. So a tennis player was a match. They hit a ball into the stands. They hit it at 30 meters per second. So they're telling us the initial velocity and the angle of that velocity. So we should be able to calculate the initial y and x velocities from that. And then they say on its way down, the ball is caught by a spectre 10 meters above the point where the ball was hit. So they do tell us the final x height, or sorry, the final y height, or the final y position is 10 meters, where the initial y position would be 0, because this is above where we hit it. And then they say calculate the time. What are the magnitude direction of the ball's velocity and impact? Well, if we calculate the time that it's in the air, we can use that time to calculate the final velocity in y and the final velocity in x. Of course, if there's no air friction, the final velocity in x is equal to the initial velocity in x. So there's really nothing to do there. But they use the same process and the same equations to calculate these things. It doesn't matter that the ball went through the apex and is now going down. The equations will give you that answer. The equations will account for that. Turns out that the time it takes the ball to get to the spectator is 3.79 seconds. And how they got that was by using the quadratic kinematic equation in y, with the final height in y being 10 meters, the initial height in y being 0. You don't see it here because they don't have it in here. The initial velocity calculated from the initial velocity times the sine of 45. So it's 30 meters times sine 45 ends up being 21.2 meters per second, times t minus 1/2 times g, which is 4.9 meters per second squared, times t squared. And then solving this quadratic equation in t gives us two answers. T equals 3.79 seconds and t equals 0.54 seconds. Now, which one do we choose? Do we choose the 1/2 second or the 3.79 seconds? Can you tell from this picture which one we choose? The answer to that kinematic equation, the solution gave us two answers, 1/2 second and 3 3/4 seconds. Which one do you think is the one where it lands at the spectator? Is it the first time or the second time? Because we're talking about when this time is telling us when this ball goes through 10 meters. Does it go through 10 meters twice in this motion? Does it pass through 10 meters height twice in this motion? Absolutely. If you draw off 10 meters here, it passed through 10 meters on the way up, and then it went up to its peak and turned around, and then it went to 10 meters when the spectator caught it. So which one of these happened first? The first one. On the way up happened first. So that has to be the 1/2 second one. On the way down happened later. That has to be the 3.79 seconds later, right? So that's how we choose the one we want. We choose the one we want by looking at the problem and saying we have two times. They're both positive times. So we need to figure out which one is the one we want. We want the one that happens second because we know that it passes through 10 meters once and then it passes through 10 meters the second time. And the longer time has to be the second time. 3.79 seconds happens after 0.5 seconds. So we know what our answer is. Our t is going to be the 3.79 seconds. And then you use that t to calculate other things. Like one of the other thing that they want to know is how fast it's going when it finishes up. Well, you can use the time with the kinematic equations to calculate the final y position, or sorry, the final y velocity, which is what they do here. They're here. They're using that 3.79 seconds, and they're going to calculate the final y velocity using this kinematic equation, which is the second one. Then they plug in their initial velocity in the y direction, which is 30 meters per second times times sine 45 degrees, which is 21.2 meters per second. Then they subtract off 9.8 meters per second squared times t. And it turns out that it's moving in the y direction, negative 15.9 meters per second. That means that our final velocity total is a vector that looks like the x vector, which is the same as what it begins as, because the x direction doesn't change, and it's your initial velocity times the cosine of 45, and that happens to be 21.2 meters per second. It's moving that fast in the x direction. In the y direction, the final velocity is 15.9, so it's less in the y direction, but it's negative also, and it's 15.9 meters per second after we calculate. Negative 15.9. That means our overall velocity is this one here that you calculate. You calculate the magnitude using the Pythagorean theorem, 21.2 meters per second squared plus negative 15.9 meters per second squared. Take the square root after you add them together, which is what they're doing right here, and you get a total magnitude for your final velocity of 26.5 meters per second. That means that this ball is actually moving slower at the end of its motion than it is at the beginning of its motion. Well, that makes sense. When you knock a tennis ball up into the stands and it reaches its peak, it's actually going its slowest at its peak. And just after its peak, it's starting to speed up again, but it hasn't sped up to its original velocity yet because it hasn't come down to its original starting position yet. So it makes sense that it would be less. Now, does that make sense to everybody? Anybody have any questions about that? Slightly different problem than the previous one, but you're solving it pretty much the same way. From these equations, these kinematic equations, when you're calculating t, if you plug in your initial starting height and your final starting height, you can actually calculate the time of flight for any object. And if you want to calculate the time of flight for an object that lands at the same height that it starts at, then you get this formula. In other words, if you say that your initial height is 0 and your final height is 0, you can calculate the time that projectile is in the air, if there's no air resistance, to be 2 times the initial velocity times the sine of theta, sine of the launch angle, divided by g. Very simple formula. And it works for any situation where you start and end at the same height in projectile motion. You can also calculate trajectory. This actually will give you a formula for the trajectory. So this will give you the equation that describes the curve of the motion of the object. So in this case, you just plug in tangent theta, g over 2 v naught cosine theta, square it down there. You leave the x's as they are, and this gives you an equation for y in terms of x. It's a function of the height it's a function for the height as x varies. X-dependent function. Obviously parabolic, it's got the x squared in there. You can also use these equations to calculate how far it goes down range. So you solve that you can actually solve that previous equation for x. And when you do, you get this equation. So this will tell you how far it goes horizontally if you fired at an angle of theta naught and a velocity of v naught. So this tells you how far it goes down in the horizontal direction. And this again is assuming that it's launching and landing at 0 height. So it's essentially being launched and landing at the same point in height, same horizontal position. And that's called the range equation. They actually use a trigonometric identity to simplify it in this version of it, so that you don't have a sine and a cosine. You just have the sine of 2 theta. That's a trigonometric identity that you may remember, but you may not, who knows. And this actually has some interesting implications. So one of the interesting implications that this has is with golf shots, with playing golf. Let's see if I can find. So we're going to play golf with a cannon. So here's the golf hole we're trying to hit right here, right? They used to let you move the statue so you could hit the statue. Maybe you can still hit the statue. I haven't tried it. You can adjust the angle here so that you can see how different angles affect the cannonball. You can also adjust the speed of the cannonball coming out of the cannon and see what that does. Oh, look, we hit David's statue, but it doesn't do anything. He used to like blow him up or something. Don't remember exactly, but it was more fun. And as we adjust the angle of this cannon down, and we just keep it at the same speed, you can see that it goes further and further down range, right? Oh, and then we hit the target and gives us the little stars. That was pretty good. So at 72 degrees, we actually hit the target. What happens if I continue moving this cannon down an angle? What do you think is going to happen if I move this down further? It's going to go further. Okay, so let's move it down 65 degrees, and it goes further, right? We move it down 58 degrees, it goes further. Do you buy your answer? You think it's going to continue to go further?
It's not going to go further forever, but
why won't it go further forever?
Because like, since it's going at a set like speed, well, it's just with the speed and the arc, there's going to be a point if it's low enough angle, it's just going to hit the ground like almost immediately when it comes out with the cannon.
Okay, good. So you're thinking in terms of the extreme. If we lower this down to 0 degrees and just fire it straight out, it's going to come down and hit the ground pretty quickly. That's the extreme end of things. And we are assuming that it's not going to make it to the target. In fact, it's going to happen long before 0 degrees that it's not going to get to that target. So let's keep going. We're at 46 degrees. Let's go to 45 degrees. 46 degrees took us all the way out to here. What's 45 degrees going to do for us? Oh, all of a sudden we're like pretty much at the same point. Let's go down to 40 degrees. Oh man, 40 degrees takes us less distance. Now we're going back towards where we started. We're actually going back towards the target. 25 degrees. Oh man, I wonder what angle it's going to be when we hit the target again. Oh, I can't go lower than 25 degrees, so we're not going to find out. So we move the target. Let's move the target out here. Let's see if we can hit this again. I'm going to guess we hit it with 72 degrees before, and we're further out. So let's say it's 65 and see what that takes us. Oh, dang, I'm almost there. Let's go to 63. So we hit it at 63 this time, looks like. So what angle are we going to hit it at again as we go down here? And it turns out that 45 degrees will be that turning point no matter what, where you go from 45 degrees will give you your longest distance as long as there's no air resistance out there. And if we go down to, see, what was it, 63 degrees? It was 63 degrees. So if we go down here to like 37, it's still too far. Go to 33, it's still too far. But if we go to 27, we hit it in exactly the same spot we did before. So at 27 degrees and at 63 degrees, you notice anything about those two numbers? They add up to 90, right? In fact, any two angles that add up to 90 will hit the same place. So if I go to 48, for example, and fire, sends my thing way out there to that furthest out one, and then I go to 42, it goes to the exact same place. Now, if you think that golfers don't know this, you don't understand golf. Because golfers take advantage of this all the time. They have golf clubs that have different angles on the face of the club. And those different angles they choose very specifically depending on what golf course they're playing on, right? Because they know every golf course that they ever play on, they've played on many times. And they know, well, I have this fairway that I have to hit. It's a really long fairway. And so I need to hit a ball that's going to go as flat as possible, because when it hits the ground, I want it to keep going. I want it to bounce and bounce and keep going down range and bouncing down the fairway. So they have golf clubs that have a very steep angle on the front. It's measured from the vertical, so it's like 1 degree or something like this. Right? Yeah, you get 12 degrees of loft, but the face of a driver is usually about 1 degree. It's a very, very flat face, so that you're almost hitting it straight off the tee. Most tees are well above the green or well above the fairway, so you're still going to get plenty of extension out there. But your angle that the ball comes off it at is not very high, and you want that because that gives it a lot of horizontal motion and very little vertical motion. And that's really good if there's air resistance too, because the more you give the ball Y motion, the less far it goes, the more the air resistance slows it down. So you hit these balls off the tee with, usually on a very long hole, you're hitting it with your driver that has a very flat face on it. And you might use like a 2-wood or a 3-wood or something if it's not a very long hole, because you don't want it to go as far. You don't want it to go into a water hazard, or you don't want it to go past the pin or whatever. But once you get in close, you start using wedges. You start using your irons, because those have an extreme angle on them. And they're going to give the ball lots and lots of loft, lots and lots of wide velocity. So when the ball comes down, it just bounces up and down instead of bouncing forward. So you pick your iron depending on the distance. And most golfers only swing with 2 or 3 speeds. They only have a few different speeds that they swing with. And they swing with those repeatedly to perfection. They are able to swing with the perfect amount of speed, and then they choose their angle based on that speed. So if you're a particular golfer and you know exactly what your speed is, the speed that you swing with, the slowest speed that you swing with, you know that your sand wedge, which is your most extreme wedge, will give you exactly 10 yards of forward movement if you swing with that perfect swing, right? Because it goes up, comes down, and bounces up and down a few times, and goes 10 yards. Then the only thing you have to think about is which way you're aiming it. Everything else is built into the swing that you've practiced a million times, so it's the same every time, and the angle that you've chosen for your club, right? So these kinds of things are very well known. One of the reasons it's almost impossible to get a hole-in-one is because you always have this forward movement of the ball. And it's easy for the ball to go past the pin, very easy when you're hitting off the tee. So the only times you ever really see a hole-in-one, well, the most times you see a hole-in-one is in a par 3 situation where you can use a wedge from the tee. And that's pretty rare. And most golfers have never hit a hole-in-one, no matter how many times they've played, because it's so difficult to do. Anyway, so that's more on projectile motion. Okay, so now moving on to a different type of two-dimensional motion, uniform circular motion. Circular motion is an interesting type of motion that we see a lot of examples of in the universe. And we know a fair amount about it since Newton came along. In fact, it wasn't just Newton that determined this, but he was really the one that put all the pieces together. Circular motion is caused by forces that are center pointing forces. So if you have a circular motion, a planet around a sun, for example, the forces that cause that circular motion are actually pointing towards the center of the motion, where the sun is. So the planet is feeling a force from the planet towards the sun. Now, that is not what most people think intuitively, but it is true. The way that we can do a little thought experiment about this, and we could do the real experiment if I didn't have tables over my circle on the floor here. But I've got this big circle painted on my floor. It's about 2 meters in diameter. And I have bowling balls over here. And if I roll a bowling ball along the edge of the circle and let it go, it'll just roll off the edge of the circle in a straight line and just keep going. However, if I ask a student to keep it on the circle after I start rolling it on the edge of the circle, in order for them to keep it on the circle, they have to keep pushing it towards the center of the circle. They have to push it on the outside of the ball, and it has to be pushed towards the center, and then it will roll around the circle. And in fact, because I chose the floors of this room to be a very hard, smooth floor, you can actually get the bowling ball to go all the way around the circle with one push. I push the ball once, and then the student just keeps tapping it towards the center of the circle. They're not actually changing the speed of the ball. They're only changing the direction of the ball. But you can get it to go all the way around there just by pushing it towards the center, just by turning it without actually giving it any extra speed. That acceleration that causes circular motion, we call centripetal acceleration. It literally means center pointing acceleration. So centripetal acceleration is the acceleration that causes circular motion. In fact, it's what causes all turning. Anytime you turn, the force that causes that turn is towards the center of that turn. That turn forms kind of a curve, and if you extend that to a circle, then pointing towards the center of that circle is the direction of the acceleration that caused that turn. So here we have an example of this in mathematically vectorially that we can use to actually prove that acceleration is center pointing. Here we have a particle that's moving along the edge of a circle, and this is its initial velocity right here. Its initial velocity is pointing upward and to the right. Some amount of time later, as it's going around this circle, its velocity is now pointing upward to the left. The velocity has not changed in magnitude. And that's what we mean by uniform circular motion. Uniform circular motion means that you're at the same speed all the time, but you're changing direction. So the velocity's magnitude's not changing, only its direction is changing. So a few seconds later or sometime later, it has the same length of its velocity vector, it's just pointing in a different direction. Well, according to our definition of acceleration, acceleration is the change in velocity. And change in velocity is the final minus the initial. So if we take these two vectors and we take the final one, which points upward to the left like this, and the initial one, which points upward to the right, the difference will go from the point or the end of the initial vector to the end of the final vector. So that's right there, our change in velocity. And if you divide that by the time, you get the acceleration. And notice which direction that's pointing. It's pointing towards the center of the circle between those two vectors. So that is the vector proof that the change in velocity or the acceleration of an object moving on the edge of a circle at a constant speed is center pointing. It is a centripetal acceleration. Of course, acceleration is a derivative of velocity. And so if we take the derivative of the velocity, the change in velocity over time, we actually can calculate a formula that gives us the magnitude of the centripetal acceleration. And this is what it is. They're actually doing this here. They're taking this limit. And the result of it ends up taking a limit. You end up getting a, let's see if they actually tell us this here really quick. I don't see they're showing this anywhere. But essentially, sorry, what's that?
You're talking about the proof for the v squared over r.
Yeah.
For us, it's right below that circle.
This one here.
Yeah, the one that you're above, it's the.
Oh yeah. Yeah, I see what they're saying. So here they're actually using a bit of geometry to do this, as far as they're using similar triangles, essentially, two isosceles triangles. And the two isosceles triangles would be this one here and this one here. And by using these two, they're essentially able to create this relationship between delta V and delta R, right? Because delta V is on one of the triangles, delta R is on the other, and they both have the same angle. By doing this, by using similar triangles, they can say that delta V equals the speed over the radius, where this V is the speed and this R is the radius. And delta V and delta R are actually vectors. Now, why is that interesting? Because if we take the derivative of delta V, it's the same as taking the derivative of V over R delta R, but V and R are constants. So they come out of the derivative. When the V and R comes out of the derivative, doing this derivative, and they're doing it in limit form. But when we do this and then we take the limit of delta R over delta T, we actually get another V there. And because delta R over delta T is V, right? When you take it to the limit, it is the speed. So then when you do that, you get V squared over R, the speed squared over the radius. So if you have an object that is moving at a constant speed along the edge of a circle, uniform circular motion, the centripetal acceleration is equal to the speed squared over the radius of the motion, very simply. That is a useful formula. Remember that. You will need it. You will use it. Here they have it in a nice gray box for you. Here's what it looks like with vectors. Your velocity is tangent to the circle that you're traveling on at a constant velocity magnitude, but a changing direction of velocity. It's constantly changing. And the acceleration at that point will be pointing inward towards the center of the circle. And the centripetal acceleration is constant as well in magnitude, but it's always changing direction as this point moves, because over here, the centripetal acceleration is pointing downward to the right instead of downward to the left, like here. And down here, it's pointing upward to the right, and so on and so forth. So both when you have uniform circular motion, or any kind of circular motion really, both the velocity and the accelerations will be changing direction constantly. Okay. So here we're going to create an acceleration equal to 9.8 meters per second by turning in a circular path in a jet plane, right? They tell us the velocity of the jet, 134.1 meters per second. They're going to tell us no, they want us to calculate the radius of the turn that will give a centripetal acceleration of 1 times g, or 9.8 meters per second squared. So we solve the centripetal acceleration equation for r, plug in our velocity magnitude, plug in our g, and we get 1,835 meters, which is 1.835 kilometers. So I think it's at about 3 Gs that you pass out without a G suit on, something like that. Watched a great video of a reporter going up in a jet with a fighter pilot, and the fighter pilot makes him pass out. He does an inside loop and makes him pass out. It's pretty funny. This reporter's just kind of talking, and he's super excited. And then he suddenly is like talking like he's drunk, and his head's just kind of falling, and then then they come out of the loop, and the reporter's just like, whoa, what just happened? He's like, that was really weird. He's like, yeah, it was just, you just passed out because and the G suit is kind of interesting. The way a G suit works is it's a full-on suit that you put on, and it's filled with fluid. It's got fluid pipes in it, essentially. And they actually inject, or it might be air, actually. I think they might use air. But anyway, they inject more air into these pipes, and it squeezes the blood from your legs upward. It essentially pulsates the blood upward from your legs up into your torso and into your head. So it keeps the blood in your head so you don't pass out when you go through these G-forces. The reason you pass out when you go through these forces is that the acceleration that you're feeling is accelerating your blood from your brain down to your legs. And then you pass out. If you do an outside loop where your head's on the outside of the loop, you have the opposite problem. You get more blood into your head and you get a headache. What's that?
When blood goes to your head, forward out, blood goes away.
What do they call it when it's going to your head again?
A red out.
Oh, a red out. Yes, because you can actually start seeing red in your eyes. Yeah, because you get too much blood in the vessels in your eyes. I didn't know they called it a red out, and I'd forgotten about that effect, but that is true. And it can actually have even more damaging effects. if you do it for too long and too high of G, you can actually burst blood vessels in your eyes and in your brain, and can be really dangerous. Outside loops are very difficult anyway, so most planes can't really accomplish them very well. All right, so some different accelerations. The Earth around the sun is 5.93 times 10 to the minus 3 Gs. So it's 1,000 times less than gravitational force on the surface of the Earth is the same. Well, 1,000 times less gravitational acceleration is causing the Earth to orbit around the sun. And you think, that's crazy. How can that possibly be? It's not less force that's keeping the Earth around the sun. It's just less acceleration, right? And the acceleration is really determined by your distance from the thing that you're rotating around and the speed at which you're going around it. And the Earth is very far away from the sun. It does have a lot of force involved because it has so much mass involved. The moon around the Earth is about the same. It's about half as much acceleration, but on the same order of magnitude. And a satellite in orbit around the Earth so that it orbits the same as the Earth is rotating, that's geosynchronous, it actually has a lot more acceleration to it. It's accelerating a lot more, right? The outer edge of a CD is 5.78 Gs. If you were sitting on the edge of a CD or a DVD while it was playing, you would pass out. A jet and a barrel roll, 2 to 3 Gs. Roller coaster, 5 Gs. So you say, well, why don't you pass out on a roller coaster? You will if it is sustained for any amount of time. But on roller coasters, it's only sustained for a fraction of a second, maybe at most. You're never in that position. And it's usually not straight down. Usually it's sideways more. Straight down is the only one that will pull that blood out of your head. So if it's a sideways force that you're feeling, which it usually is, it's usually partially sideways force, then you're not going to feel it. And you really do have to feel it for a few seconds. So, I actually went on a roller coaster as a kid that's still there actually in California. It's called the Tidal Wave. And it's just this huge loop. It's like 6 stories tall. And it just goes you just go up on this really high tower, and then you go through this loop, and you go up on another high tower, and then you go backwards through the loop, and you just keep going back and forth through this loop. And we were there, me and my best friend were there. Just nobody was at the park. It was a school day. We were cutting school. And so we went on this thing like 20 times in a row, and we got off. We couldn't walk because we had shin splints in our shins. It had actually fractured. It had created micro fractures in our shins from all of the G forces we felt over and over again. We were like limping away from this. We had to go and like sit down for an hour for our legs to stop hurting enough till we could walk. It was pretty awesome. All right. So circular motion, we're going to think more in terms of R and theta. We're going to think in terms of rotation rather than linear motion. And so we're going to measure our position using the sine and the cosine and an angle. And the angle is going to be related to our angular velocity or angular frequency. In other words, how fast the particle is going around. And we're going to come back to that on Monday. When is the homework due? I don't remember. Wrong class. Calendar. So we say we've got the homework due on Tuesday, so we'll come back to this and finish up on Monday. So have a great weekend. I didn't post another lab, but I'll do that next week. So anyway, have a great weekend.
Have a good weekend.
We'll see you later.
Have a good day.
Thanks. See ya.
See ya.